Okay, we'll start so we can save a few minutes. So our first keynote is Jon Gibbins, certainly a stranger to none of us. So he's worked in the energy engineering, fuel conversion, and CCS for a substantial number of years, initially in industry and then in academia. He's a chartered engineer, a member of the IMEC, a fellow of the Institute of Energy, and a professor of carbon capture and storage at the University of Sheffield. Since 2005, he's played a leading role in the UK CCS Research Centre, building and growing this center as an inclusive and open virtual national hub, and helping to start now mainstream UK initiatives on industrial decarbonization and CCS clusters. So I had the pleasure of meeting Jon several years ago at Sheffield. He was very kind to show me around. I wish I could have returned the favor and showed you around here, but perhaps next time. So with that, I'd like to invite him to give his keynote lecture on the global picture on capture from power generation. Professor Gibbons.
Okay, thank you. And I'm sorry about the cat, but it'll be quieter this way if she sits on my shoulders. So I'm going to talk a bit about the current environment in which CO2 capture from power generation has to work, which I think is a change. So mentioned that the cost of renewables is no longer a barrier, and CCS now has to work in an environment with a lot of renewables, and I think it's important to understand the effects that has, and also how CCS can complement renewables. So if I go down. So I'm going to use an IEA scenario, sustainable development scenario, that was developed in 2017, but is still valid, although perhaps the timescales changed. It includes quite a lot of details on what happens with carbon capture and storage power plants, which makes it very relevant for what we're doing. And the scenario has the characteristic of turning emissions, global emissions, round and reducing them down to about 20 gigatons per year, a level that we didn't see only saw previously in the 1990s. And that's as a preparation for then making the big shift down to net zero in phase 2. And then very, very likely now, if we want to limit warming to 1.5 degrees, a net negative phase, which will go on ideally from about the middle of the century, a bit earlier than shown here, for an indefinite period, probably for another century at least. So 3 phases. Phase 1, we've got to do some major reductions and lay the foundations for actually then getting to net zero, but we do need to go beyond, almost certainly go beyond net zero to net negative. Virtually all of the IPCC 1.5 degree scenarios now show that we're locked into a phase of net negative global emissions. And as you can see, potentially quite large amounts too. Now, in this scenario, the reductions are achieved by cutting coal emissions. So this is energy use from coal. This is this sort of business as usual. This is the sustainable development scenario. Oil, business as usual, big cut, sustainable development scenario. Gas carries on increasing, but not as much as would be expected, and basically levels out, and then obviously we'll have to drop. So I don't see any reason that this has changed. Coal is still getting a lot of attention as the villain of the piece on CO2 emissions, although in fact it's not much more than oil in aggregate now. One of the features you will see, though, in this scenario, and I think this again is something that we can expect to see delivered, is that when you obviously get this downward pressure on demand for oil, demand for coal, and indeed in some respects demand for gas, is that you see that the prices are soft. Essentially, for all of the commodities in this sort of market, the expectation is that the prices won't increase rapidly. In some cases, they'll go down. And that, of course, has significant implications for carbon capture and storage, power generation, because these are the fuels that will be used in CCS power generation. So, as I say, scenarios that any scenario, not just this one, that show severe downward pressure on emissions and lack of unabated use will also naturally tend to give low fossil fuel prices and hence relatively low CCS costs. In this scenario, there was quite a lot of carbon capture and storage by this endpoint, which, as I say, may be closer than 2040 now. There was about 1.6 gigatons per year of CO2 stored, which is about 40 times where we are at the moment. That might be 100 large sources or clusters. So obviously quite a lot of work to do. You're talking about between now and then a cluster every not so many months to get that to happen. But nonetheless, it's not an unbelievable number. On capture, on power, this scenario included 375 gigawatts, which is roughly about 1,000 times the 300 odd megawatts that we've got now, and obviously plus industrial sources. In terms of what would happen on energy use, you can see that we finally get away from a level of about 80% of total energy coming from fossil, which has been the trend globally for many, many years now. We actually reduce the percentage of total energy coming from fossil down to 60%. And we increase the fraction of fossil fuel used with CCS from essentially zero now up to about 10%. And it's very relevant to think what will happen after that as we go to phase 2 to net zero. And one thing I can guarantee that will have to happen because we get to net zero is that by the time we're at net zero, 100% of fossil fuel use will be with carbon capture and storage, either directly or indirectly by taking the CO2 that's produced when the fossil fuel is used back from the air. It has just the same effect as capturing the CO2 at point source. And I'll say a bit more about that. So that's using biomass with CCS or possibly direct air capture. And direct air capture, I think, doesn't have the limitations of natural systems, so may become the marginal capture method for taking CO2 from the air. Now, we know that 100% of the fossil fuel will have to be captured to get to net zero. That's just a straightforward definition. Indeed, it's not only required, it's probably the only way you'll get to net zero. What we don't know is how much of global energy will be coming from fossil fuels at that period. And obviously, to some extent, that's going to be influenced by how much CO2 we can capture. And effectively, our competence at rolling out large amounts of CCS will determine how much fossil fuel can be used. So it's pretty important. After we get to zero and we want to go negative, obviously we'll have to use CCS with capture on as much biomass as we can use, as we can get hold of without disrupting natural systems and food supplies. And then the only other methods are engineered forms, either enhanced natural methods, weathering, or direct air capture. This is for a long period as well. We're talking about the climate not stabilizing for tens of thousands of years. So the permanence of these removals is very important. So trees will remove CO2 from the atmosphere, but they won't necessarily hold it for long periods. And I think it's very important to consider the synergy between planting trees, but then also making sure that at the end of their natural lives, they don't just re-release the CO2. Going back to the topic, which is power, this is electricity generation by source over this period. Bearing in mind the timescale may not be right, but nonetheless, if you want to hit this sort of reduction in emissions, then a number of things have to happen, and particularly fossil generation, unabated, which is the brown from coal, has to go down. In this scenario, gas, as we've seen, doesn't decrease significantly. nuclear grows, hydro grows, wind grows a lot, solar grows a lot, and other renewables. So we see an increase in total electricity generation, which is very important because a lot of other activities are going to use electricity as a decarbonized energy vector. But we see CO2 emissions from that electricity production dropping fairly rapidly. This is the energy that's produced. This is the capacity that produces it. So obviously for intermittent renewables, solar and wind, there's relatively more capacity than there is energy generated. Similarly for CCS on coal, there's as we'll see, I'll discuss it a bit more, quite a lot of coal capacity, not so much coal with CCS capacity, but that actually generates a lot of the energy. For gas, there's a lot of still of energy generated from unabated capacity, though even there, the gas CCS has a higher load factor. So the amounts, about 210 gigawatts of coal power in this scenario, a lot of this in China, and that's about 15% of current Chinese power plant capacity. I have every confidence in my Chinese colleagues being able to deliver that if required. It'll be a political decision for them to do it, but they built the plants in much less time than this. They can certainly add CCS to 15% of the fleet. Globally, and not much of it in China, I would expect 165 gigawatts of gas power capacity. Again, doable over that period, a lot of it by retrofits. So that's the sort of scenario. Another way of looking at it is that we see total electricity capacity increasing significantly as generation goes up by nearly 50%. And the biggest part of that increase in capacity is wind and solar. I think that, again, we've seen at least that sort of increase. I think if anything, we'll see more. But also, to back it up and just going over to the diagram, you can see that total firm capacity increases. And this is needed to support that amount of electrification when you've got very large amounts of wind, solar, and other intermittent renewables. You do need the firm capacity. And some of that comes from increasing hydro and nuclear, but unabated fossil capacity decreases by 20%. And some of that is made up by natural gas, but some of it's made up by CCS capacity. So that's what we're seeing. And obviously, as I said, to go to net zero, this unabated fossil capacity, which goes down, will have to go down to zero. You can't have any fossil emissions. So in the longer term, this trend will have to continue and be accelerated. Looking at a little bit more detail at coal, because I think it's a good model for what will happen also to gas in the second phase. This is where we were in 2016, not very different now. We've got about 2,000 gigawatts of coal capacity globally, with an average load factor of about 50%. Rather less than half of that is closed in the scenario. Some of it's fitted with CCS, 15%, and that runs with a load factor of 69%. The rest of it essentially is turned into peaking plant. It's there, it's been paid for. You wouldn't build it as peaking plant, I don't think. It'd be far too expensive, but given it's there, it's reliable. In many cases, you're not even reliant on a gas transmission system. You have a stockpile of coal, which you can use, so that's very good. It's run as peaking with an average fleet load factor of 11%. And that shows even more here, as I said, this is the total generation from coal, the energy now. There's a big reduction in energy, electrical energy produced from coal, but a lot of what's left is from CCS plants, and there's a small amount from the peaking plants. So a lot of capacity, not doing very much generation, but providing an important service to the grid. Now, looking at this in a bit more detail, and I'm going to use a UK example here. Again, it's a fairly old example, but I think things don't change, because what we're looking at here is the generation from a lot of wind power in the UK in 2030. And obviously we don't know what the wind will be blowing in January 2030. So we're using historic wind data from January 2000. And it's assumed there'll be 43 gigawatts of wind. In fact, I think there'll be rather more than that. Current targets that have 40 gigawatts of offshore wind plus 14 gigawatts at least of existing onshore. But again, the trends will be the same. And what you see is a very, very peaky output, some quite rapid changes in output, and some periods when you have very, very little wind at all. And this was not a bad January. In the UK, January, very little solar power, and we sometimes get anticyclones where we get very nice, dry, cold weather with wind for several weeks. I usually get very good snow then. You go and have a lot of fun outdoors. It's a little bit like being in Scandinavia. It doesn't last for long. We get rain and wind and lots of generation, but we do have to fill in these blank periods. And how do we fill it in? Well, we see a mix of nuclear, which will still be there. And then in this scenario, there were a range of other different options, some of which won't be there, such as don't expect there'll be much coal with CCS. But you see a whole set of different plants coming on, filling in the gaps, and last of all, an abated peaking plant. And I think this will still follow. In the UK, we'll see lots of periods when all sorts of different forms of generation just don't run at all. The grid is being set up to run, in fact, without any firm generation, just running with essentially grid stabilization measures and nuclear. We won't need any fossil plant with CCS or without, but then at other times we will, just to meet the energy demand. So this is a feature of the UK. Obviously, you'll get something a bit different if your intermittent renewables are mainly solar, but you will still get variation, significant variation. And you will also then get variation in demand, which we'll look at here. So this is a annual demand profile, blue curve, for UK demand. So it's never less than about, expect to be less than about 30 gigawatts, and it will peak up to about 70 gigawatts at times. So this is our demand. If anything, will tend to go up as we move on for electricity for heating, and also air conditioning now in the summer in the UK will become more frequent. Now, if you take away the wind from that, and this is the instantaneous wind that's blowing, you end up with another curve which is even more variable. And so at times, we've actually got too much generation, as I say, because we expect more wind than was actually used in this scenario. There'll be times when we don't need anything at all but wind. And then there are other times, as I said, when there's very, very little intermittent renewable generation for short periods, when we have to meet the whole load with alternative methods. And this is the UK, but I think you'll find qualitatively similar trends in a lot of places. So what does that leave you? Well, as I say, there's the intermittent renewables, then essentially you have to meet the rest of the demand. So there's some near baseload, no actual baseload. As I say, sometimes we've got excess intermittent renewables. If you've got nuclear plants, you've got to decide whether to switch those off or put the brake on a wind turbine or throw the switch on a solar array. It should be an easy question, but we do seem to have people who want to turn off nuclear so they can run renewables. So it doesn't make sense, but perhaps that'll get sorted out. But for our purposes, we need to think what's happening then to CCS plants that are providing dispatchable power. Note this is at a range of load factors. So this is 100% load factor. I've shown it going down to 20%. You might want to consider alternative methods. So you've got quite a lot of capacity running at load factors between 20 and 90%. And if you remember the last slide, running with all sorts of erratic operating patterns. And by and large, not operating at minimum stable generation, but just getting switched off and having to restart again. Sometimes it'll be ramping rapidly to meet a foreseen change in wind, but as I say, it'll be off and on with a pattern set by the weather. Then there's also, and these areas represent the total energy, there's also a very small amount of energy, but actually still quite a large amount of capacity that's providing peaking plants. And I put this fairly arbitrarily at 20% load factor, but most of it is below 5% load factor. And that's really important. If you don't have this, then your electricity grid falls down. And we see the sort of situation that we saw in Texas in the winter. So this is really to be avoided. This is an important plant, but it's not running very much. It's not generating a lot of energy, and it's not generating a lot of CO2. So this is the sort of trend that we're expecting to see. I think it'll be very interesting how it plays out. They're only illustrative trends, but I expect them to be general. I expect the load factors that are shown here, if anything, to be reduced in reality, and certainly reduced as we move into even more renewable generation in the future. So, capture from power plants, what are the characteristics? So this phase one, where we're seeing the first major reductions and laying foundations for future generation, we expect to see capture on dispatchable power plants with all fuels, probably limited base load. Capture may be stopped for short periods to allow more power to be sent out, but all the plants have to switch on and off. Getting to net zero, you're going to be looking at these peaking power plants, because you've got to go for all sorts of emissions. I don't think that you'll actually, on many of these, capture a lot of the CO2 at source. You want low load factors. The running costs can be very high, but it's important to keep the capital costs as low as possible. So options there include hydrogen with storage. It's very important that you have hydrogen storage, otherwise your capital costs will go up. Ammonia, we've heard mentioned, biofuels, or synthetic fuels made from CO2 taken from the air. But actually, if you're going to do that, and this is something that hasn't received enough attention, but it's an obvious way to do it, you can just carry on using fossil fuels, and then instead of taking CO2 and turning it into fuel, which is relatively expensive, you can just bury it, put it away permanently, return it to the geological storage that it came from. So fossil fuels plus carbon dioxide removal via BECCS or DACS is also a possibility to achieve net zero with these peaking plants. Then for the net negative phase, we'll require obviously carbon dioxide removal at very large scales, and that could also affect power generation because we'll want to get BECCS on as much biomass as available, and that can be purpose-grown biomass, certainly biomass from waste. So electricity in that case can become a byproduct. The negative emissions may well be a lot more valuable than the electricity, particularly when you've got excess renewables. I mean, if you've got excess intermittent generation, more electricity than you can conveniently use, the value of electricity is essentially zero or even negative. But the value of removing CO2 from the air can still be very significant. You may also be able to integrate electricity production and DACS. You may need some electricity to run direct air capture, but you may also be able to use low-grade heat. You can certainly share CO2 transport and storage systems. And it's obviously a very good time to run direct air capture when you're not running CCS power plants, because by definition at those points, you've got plenty of electricity. So you may want to use that to drive the DACS and run it inversely with power. So just drilling into a bit more detail, point we've already made many times, if you're in phase one, power plants have to be dispatchable. As the load factor reduces, obviously capital cost becomes important, and thermal efficiency has a secondary impact, especially at lower fuel costs. You do have to be able to meet periods of peak emergency demand with these dispatchable plants as well as with the peaking plants. There may be some benefit from time shifting the capture penalty if you can do that. When you're heading for net zero, perhaps not in this first stage, you will need to capture as much CO2 as possible, maybe as much as 99%, which is effectively all of the fossil CO2 from natural gas, or you have to be able to upgrade the plants to do that. People are very concerned about other pollutant emissions as well as CO2. And in some areas, CCS raises questions about water demand, although the answer to those questions is just inappropriate engineering of the plants. Except in some cases, and I think we'll hear more about that, you may well be able to harvest some water from CCS, either in the capture plant or also if you're injecting water into saline aquifers, you may use the produced water. So just looking at some characteristics, these are from a published study by Wood, formerly AMEC Foster Wheeler, for our energy ministry. This information is available. You can download all of the details and the cost calculation spreadsheet. These are their estimates of the performance of various CCS power plant options. And we've got the levelized cost of electricity, which is the total height of the bar. We've got the size of the plant, which is the diamonds. Different size of plants, quite small plants for biomass, larger plants for fossil fuels. And then I've also added the availability and load factor, which is either 85 or 90%, and also the lower heating value efficiency for a new plant, to give you some indication of that effect. So what we see is, compared to the default gas post-combustion technology, the predictions, and I'm sure we'll hear something different a bit later in the conference, the predictions were that, in fact, this was no more expensive on capital cost and probably, according to these predictions, better than supercritical CO2 cycles or molten carbonate fuel cell cycles. Now, these were both more efficient than post-combustion capture, but that wasn't enough to make a radical difference to the overall cost, levelized cost of electricity. And of course, as I say, you can easily see that if you were to be running the plant at, say, 50% load factor, capital cost contribution goes up, then the capital cost will become even more important. And then also these models actually assume fairly high natural gas prices. As natural gas prices reduce perhaps to half the levels used here, again, you'd see less impact from the efficiency. So some interesting pictures there. Coal is always more expensive. I don't think we'll be seeing any new coal plant. Gas conversion to hydrogen, which is then burnt, is penalized both on capital cost and on efficiency. The only way this works, I think, at least where you can do conventional capture, transport of CO2 and storage, is if you run this system at very, very low load factors and size the hydrogen plant accordingly. So for any of these units that capture CO2, the capital cost increases inversely to the load factor, whereas potentially with hydrogen plus storage, very important to remember, plus storage, then the capital cost may not increase with reducing load factor significantly. The turbine cost would increase, but that's a very small part. On biomass, I said that's very important. We're seeing high capital costs and high fuel costs. These give nominally high levelized costs of electricity, but there's no credit for the carbon dioxide removal from the atmosphere. And that credit could be of the order of, in our currency, £100 a ton, which would be about £100 per megawatt hour. So that would significantly reduce these numbers and bring them down to this sort of level. And it's very important when you're using biomass with CCS to include that credit. Now, just a little bit more on post-combustion carbon capture, because at the moment it's the default technology. This was a study done for the World Bank for a project in Mexico. It's somewhat unusual in that the consultants, Nexant, approached a number of proprietary solvent manufacturers and asked them to give details of energy performance and capital costs. And when they put the results into a standard model, there was essentially no difference between the proprietary suppliers, most proprietary suppliers, and indeed not very much difference from what would be yesterday's solution of 30% MEA. So interestingly, when you get down to it, particularly for natural gas, where you're not very sensitive to the energy consumption, there appears to be little difference between the Amine offerings on when you apply a standard method. If you're more interested in post-combustion capture, which the default would now be 35% by weight MEA, which is a little bit less energy, more compact plant, then we have an open access study there, which is available to look at. Capture levels are also important, and we've just recently seen published levels of capture in the high 90s, above 95% from actual tests at Test Center Mondstadt, so that's very good. And we've also verified that, mimic that using modeling at University of Sheffield. And this is taking capture up from 90% to 99%, and the energy requirement, which is the green line, goes up slightly, but not very much. And when you compare it with air capture, it's quite a good deal. I said you need to stop and start plants. With post-combustion capture, an easy way to keep on capturing while you're doing that is to store the solvent. Store lean solvent and rich solvent, run it through the absorber, and you can keep the same high capture levels all the time. Some things going on globally. The UK, as I say, we've got lots of different options we're looking at, but it's changing rapidly. It's a competitive situation. The US, there's multiple feed studies going on for both gas and coal plants. Petronova was a coal plant with CCS that was run but not now operating. And they had some bad experiences with gasification. Canada, there's the Boundary Dam coal plant operating. Netherlands is looking at post-combustor and waste. China is considering coal post-combustion capture retrofits, and they're actually helping Australia as well, the Huaning Group, helping Australia with a proposed retrofit. And Japan has a biomass retrofit plant. And there's a number of references, but as I say, it's very hard to keep up to date with what's going on. It's a fast-changing situation, and it's competitive as well, so you don't hear everything. So, final words. Power plants with CCS are very important to help deliver net zero emissions. Now they'll, I think, mostly all need to be dispatchable. There may be retrofits on all sorts of power plants, coal, gas, biomass, and oil plants. I'd expect new build gas and biomass plants. Currently, most of the projects being talked about use post-combustion capture using amines, but any technology that can offer reduced capital costs will be competitive. Efficiency, though, I think is going to be less important. However, the capture level is important. We're heading for net zero. The alternative, if you don't capture it on the power plant, is direct air capture or BECCS. And then pre-combustion capture for power. In principle, it looks attractive because you've got concentrated CO2, but it does appear to be more expensive, except possibly hydrogen for peaking plants with storage. And also, we will expect to see hydrogen use in turbines for power generation where you can't do CO2 transport and storage. So it will happen, but it's not necessarily the cheapest way. Okay, thank you very much.
Thank you, Professor Gibbons. So to stay on time, I think I'll collect all the questions till the 45-minute panel session, if that's okay. So please, please stay on the line. To try and stay on track, we'll introduce our next talk, which is on carbon capture and convergence using CST. And the speaker is Professor Lipiński from Australian National University. He received his PhD in mechanical engineering, mechanical and process engineering from ETH Zurich, and his habilitation also from Zurich in 2009. So these introductions will be quite short because their talks are only 15 minutes. So their complete bios are in the conference website. So please look at those. It's an impressive group of speakers we've assembled. So Professor Lipiński, with that, I'd like you to go ahead and get started. Thank you.
Thank you very much for your kind introduction. Welcome, everyone. So I'm going to talk about the solar thermochemical CO2 capture and energy storage via calcination, carbonation, chemical looping. Now, this type of research development falls into the category of solar thermochemistry. In the solar thermochemistry, we have three main areas. One is solar production of fuels from water, carbon dioxide, or by processing carbonaceous materials. Another one is production of chemical commodities and processing, such as calcination of calcium carbonate or separations of gases. And the third column, the third area that is not shown in this graph is thermochemical energy storage that matches concentrated solar power plants or industrial processing systems that are powered by solar thermal energy at high temperatures. Now, the solar-driven calcination carbonation chemical looping is a closed loop process, as the name says. So we use a metal oxide, and this metal oxide or sorbent is generated in the endothermic calcination step of a carbonate. Now, this process is highly endothermic typically, and it can be matched with the high temperature solar thermal heat provided by solar thermal systems. Now, the sorbent is cycled then to the second exothermic carbonation step, in which we react it with carbon dioxide coming from various sources. In this slide, you can see two colors. You can see labels in two colors. The red labels refer to the application of the calcination carbonation chemical looping for solar CO2 capture. But the same process can also be designed for solar thermochemical energy storage. The reactions are highly endo-exothermic. There is a lot of energy that can be stored in this reaction. Now, depending on the application, we may have different streams of carbon dioxide into the system and out of the systems. For example, if we just separate CO2 from flue gases, this pure CO2 can be used for production of solar fuels. For example, towards solar synthetic gas for renewable kerosene for aviation. Different metal oxides have been proposed for this process: calcium, strontium, manganese, magnesium, barium, and others. They have, as I mentioned already, high theoretical storage and capture capacity. For example, for calcium carbonate, this is 1778 kilojoule per kilogram, which is 3 to 4 more times the energy density for commercial molten salt storage that typically matches concentrating solar power plants. Calcium carbonate is abundant, it's low cost, but there are challenges with the loss of reactivity and material degradation, and we need to develop a high temperature solar reactor technology, which is not trivial. Now, I will guide you through this process and different challenges in realizing solar-driven chemical looping processes by considering different length scales, from the smallest scales typical to sorbent particles through the groups of particles such as packed beds or fluidized beds to solar reactor level. And I'm going to show you some examples. So let's start with analysis that are typical to sorbent particles. Typically here, at this level, we are interested in investigating the properties of individual particles, such as their internal structure, porosity, as well as the overall size, on the extent of chemical reactions, both for the calcination and carbonation step. And here we have used combined numerical and experimental methodologies. On the numerical side of things, we have developed mass and heat and mass transfer models coupled to chemical kinetics of calcination and carbonation with realistic properties corresponding to those of single calcium carbonate or calcium oxide particles. Now, modeling itself can be quite off of actual results if our input data contain some uncertainties. So it's important to conduct also experiments to validate these models. We have developed a quite fine setup that uses a thermogravimetric analyzer in which we have individual particles placed in the crucibles. And here you can see the particles actually after cycling, when they develop, after calcination, when they develop a crust of carbonate around those particles. So these are two examples. You can see here the weight loss for a typical experiment. So first we have calcination, and then we have carbonation. We have here also two signals on the mass spec for carbon dioxide and for water. There is usually water in the initial step of this multi-step process that is water bound in the structure of the carbonate itself. Now, when we now compare the original simulation results to the experimental results, we can see that, and this is not surprising, there is typically some discrepancy. So our model, the sophisticated model, was tuned to by scrutinizing some of the input parameters and properties, and eventually we were able to match the experimentally measured results. In this case, this is the overall extent of the calcination reaction, followed by the extent of the carbonation reaction. So the match is good, and it was tougher actually for the carbonation step than for the calcination step. Once the model was adjusted, we were able to predict the behavior of these individual sorbent particles as a function of their size, as a function of the composition of the reactive gas atmosphere, with variations of the CO2 concentration from 25 to 50 to 100% for particles of selected size. So now let's move on to the next scale. I'm going to show you this next scale that is weakly coupled to the smaller scale, which means we follow the hierarchical coupling process in the overall analysis, but the links between the scales are still very challenging. We deal here with very disparate length scales. Now at the group of particle levels, such as packed beds, we have developed computed tomography-based methods where we can measure the morphology, geometry of packed beds directly using by scanning these samples of packed beds, reproducing their geometry in computer memory, and then using this actual geometry in direct pore level simulations for hidden mass transfer characterization. I'm showing here to you two plots where we actually studied radiative transfer. I'm talking about solar thermochemical looping, which means the process is driven by concentrated solar radiation, and radiative properties are very important for precise modeling of the systems. So with this approach, we can actually achieve quite good accuracy of the radiative and other characteristics of such packed beds that can be used in simulations of scale-up systems at the reactor levels. And now I'm moving on to the next length scale, typical of solar reactors. There have been many prototypes of solar chemical reactors for solar calcination. So I'm showing only 4 examples here, but there are many more out there in the literature. For example, the direct irradiated solar thermochemical reactor developed at Paul Scherrer Institute and ETH Zurich around 2001 to 2004. Here we can see this reactor being tested in a solar furnace. The second generation of the reactor developed at Paul Scherrer Institute was a indirectly heated reactor, which means solar radiation was hitting the surfaces of the tubes and particles were flowing through those tubes. So it was kind of a rotary kiln with indirectly heated particles. And here we can see the front view of this reactor after experimental testing. We have here 2 more examples of the reactors, a mini rotary kiln and a reactor with a fluidized bed that is where particles undergo calcination. Now, there are no reactors that have realized calcination and carbonation in the same device. We have addressed this challenge, and we have designed a reactor that should be able to work for both calcination and carbonation. This reactor has a conical aperture through which concentrated solar radiation enters a solar receiver. Then in the space between the 2 concentric cylinders, we have the reacting particles, and through which gases are flowing. Depending on the reaction step, we will have different gases flowing through this reaction zone. Again, we developed a comprehensive heat and mass transfer model based on the continuity, momentum, energy equations coupled to chemical kinetics of calcination and carbonation. This model was implemented in ANSYS Fluent with extensions to account for radiative properties for reaction kinetics through user-defined functions. And here I'm showing sample results. So the temperatures for calcination, the onset of calcination is slightly below 900 Celsius. So we can see that corresponds to the red color in this schematic. We can see that under constant cooling, because we have assumed that we have always cold gases at the input during calcination, purge gases, it takes more than 3 hours actually to achieve the temperature that is suitable for calcination. So obviously this operational strategy requires further optimization, and we will address it now in an experimental campaign with an actual prototype rather than first starting with this extensive modeling. We can also predict the extension of the reactions. Here I'm showing the overall extent of calcination. The red color means the material is completely calcined and ready to take on CO2 in the carbonation step. These simulations are extremely time consuming. Even with vast computational resources, 3D geometries in presence of nonlinear kinetic effects and radiative transfer effects require days to complete single cases. So now let me show you the experimental setup that we have prepared to test the actual reactor prototype. It will be tested in the new high-flux solar simulator, which consists of 18 radiation modules. The reactor will be placed in the focus, and we will have different gases flowing into the reactor depending on the process step, calcination or carbonation, where we can emulate any composition of flue gases or other exhaust gases from industrial processes. And the outlet gases are analyzed by a mass spectrometer, which will help to close the mass balance in the reactor and also calculate its efficiency. So here I'm showing the photo of the new high-flux solar simulator. As I mentioned, it consists of 18 radiation modules. Each module has individual cooling and power electronics. And on the right, you can see the parts, the open reactor actually without insulation. So you can see the cavity below, you can see the gas manifolds for inlets, outlets, and it will be placed in the focal plane in the compartment of the solar simulator, which is equipped with flow controllers, where we have access to most typical gases that are needed for experimentation in thermochemistry. To conclude my presentation, the calcination, carbonation, chemical looping processes are thermodynamically compatible with state-of-the-art solar concentrators. It's not difficult to achieve the temperature of calcination of 900 degrees Celsius. This is the actual state-of-the-art solar tower technology, or even now beam down technologies, which allow placement of the reactors at the ground level, and this avoids many complications how we transport material to the solar tower. The two-step process scales up well because the materials are low cost. These are like calcium carbonate, but they are limited only to point sources of carbon dioxide, which means these processes are suitable for carbon capture, but not for direct carbon removal from air. The reasons are thermodynamic. The concentration of CO2 in the atmosphere is so low that basically flowing large quantities of air through our packed bed of carbonate-based materials would lead to thermal losses and also to mechanical losses. So most studies have focused on calcium oxide-based chemical looping for this application, and sintering and sorbent activations are still a remaining challenge. This challenge can be addressed partially, at least this has been proposed, by doping into the sorbent or addition of steam. There is an ongoing work led by the University of Adelaide on the effect of calcination under a steam atmosphere, and the results are very promising. The sorbent is not deactivating to the extent we see it without any steam addition, and of course fluidization, which is a major change from packed bed configuration in solar reactors. And I said that numerous solar reactors have been developed to demonstrate the calcination process, but actually beside our reactor at the ANU, I'm not aware of any other solar reactor that is capable of running both calcination and carbonation in the same device. There have been numerous benchtop studies to demonstrate this process as a pre-step towards solar demonstration. And of course, this process has been demonstrated at an industrial level, pilot level, but without the solar energy input. So there is still to do in this area to couple this very disparate length scales and challenges characteristic to each of these length scales, from sorbent characteristics to reactor design, and then overall solar plant optimization. I have not discussed here the solar plant optimization, as this is work in progress here. We just have studied optical systems that may be suitable for the system, but this is not yet enough to present at a conference. So I hope we can share some new results in the near future on our research at the plant level. So thank you very much for your attention.
Thank you, Professor Lipiński. So again, in the interest of time, we'll move on to the next talk. So the next talk is Mohammed Juaied from Saudi Aramco. He's a research scientist consultant for the technology, strategy, and planning. His work is focused on the development of climate-related technology strategies to support Aramco's sustainability business objectives. There's a PhD from UT Austin in amines, and with that, Mohammed, you want to take over?
Do you hear me?
Yes, we can.
Yeah, good afternoon all. Thank you, Bill, for the kind invitation. And I would like also to thank the organizers for the invitation to speak at this conference. Today, I am delighted to provide you with a review of the conventional amine scrubbing for CO2 capture. My presentation will be in 4 parts. Firstly, I'm going to provide you with a general overview of the amine scrubbing and the background. Then I am going to talk to you about important process improvements for absorption and regeneration systems. And finally, I'm going to discuss the important properties for amine selection and conclude with a summary of important representative absorption liquids. Amine scrubbing for CO2 capture is based on the common absorption stripping process for removing H2S and CO2 from natural gas and other fuel gases. This figure shows the process patented by Bottoms to sweeten natural gas with notation for use of piperazine to capture CO2 from coal-fired fuel gases. Hundreds of plants have been constructed using this process for acid gas treating of natural gas and hydrogen with MEA or other common amines. More than 30 CO2 commercial applications for flue gases from gas-fired power plants are available, with more than 20 employing floor technology using 30% MEA. The largest of these was the gas-fired 1,000 ton per day power plant at Lubbock in 1983. MHI, they have more than 10 plants that use KS1, proprietary amine solvents. Only a few plants have been constructed to capture CO2 from coal-fired flue gases. Lamos Technology owns a process that used 20% MEA in 4 operating units. Council of Shell, they started operating an amine system at Boundary Dam, Saskatchewan in 2014. MHI also, they started a 4,800 ton per day system, capture system in 2016 at Thompson, Texas.
Mohammed?
Yes.
Sorry to interrupt. Can you turn your camera on?
Yeah, I'm sorry. Yeah, do you see me?
Yeah, good. Thank you.
I'm sorry. 4 classes of aqueous liquid absorbents can be considered for CO2 absorption and stripping. They differ in the heat of CO2 absorption, kinetics of CO2 absorption, and the intrinsic CO2 stoichiometry. The hot potassium carbonate process is offered in a process by UOB. It operates isothermally near 100 C with the pressure swing regeneration. But it's because of its heat of absorption is low, it's unfavorable for thermal swing regeneration. Tertiary amines such as MDA are usually used in blends with rate promoters such as piperazine. Hindered amines also like aminomethylpropanol can be used alone or in rate or in combination with rate promoters. Secondary or primary amines such as MEA and piperazine can be used alone or as rate promoters with tertiary hindered amines or potassium carbonate. This table compares the applications of amine scrubbing and CO2 capture process when it is adapted. When amine scrubbing is adapted for CO2 capture, the amine process must tolerate oxygen in the flue gas. Flue gases contains oxygen. They also have to remove CO2 at lower partial pressure and lower total pressure. They also have to deal with much larger volumes of gas. And they need to be also more energy efficient. This figure shows the heat duty of select commercial units using capture and combustion gases from 1976 to the present. At Lubbock in 1983, the reboiler duty decreased with the substitution of 30% MEA for 20% MEA. At the MHI plant in 1999, 30% MEA was replaced with KS1. At newer MHI plants, at the MHI plant in 2009, additional energy savings have been resulted also from stripper process modifications. These innovations, presumably, and plus the absorber intercooling, were applied by MHI at their plant in 2011, Plant Berry, and they were also implemented at Thompson, the Petra Nova project in 2016. The Council plant at Boundary Dam started in 2014, as I mentioned, achieved energy savings with a new aqueous amine solution and with the use of stripper modification, a lean vapor compression at the stripper that I will discuss in the next few slides. This table compares the development timeline of limestone slurry scrubbing process for flue gas desulfurization and compares to that of the amine scrubbing for CO2 capture. The two technologies, the FGD and CO2 capture by amines, they were both identified as the initial technology of choice. But because of almost insurmountable difficulties or the high cost projections, R&D activities initially focused on advancing promising alternative solutions. The limestone slurry technology is now basically the dominant technology for flue gas desulfurization, and it's possible and it's probable that the amine scrubbing will be the dominant technology for CO2 capture from coal-fired power plants, and possibly for other applications. CO2 absorption is exothermic, as you can see here in this figure, and results in a temperature bulge in the absorber. And the higher solvent temperature limits the maximum capacity of the solvent. So cooling the solvent at intermediate locations in the column, intercooling, what we call intercooling, is going to help by removing the heat generated, which can help mitigating the capacity and driving force limitations. This figure basically shows that the trade-off of total backing area with the liquid rate. An isothermal absorber would require less backing and a lower liquid rate to achieve the same performance. In many cases, intercooling may be used to reduce the absorber backing cost and increase the rich loading. As you can see here, at a given lane loading and infinite backing area, there is a minimum liquid rate, L over G. And similar to the distillation process, the economic optimum backing area probably will happen at a liquid rate between 1.1 and 1.3 times the minimum liquid rate. This figure shows the potential effect of intercooling on the liquid rate. As you can see here, this is with 8 molal bibrazine at 4% inlet CO2 concentration at a critical loading of 0.21, as you can see here, more CO2 per equivalent bibrazine. The minimum liquid flow rate is almost 3.5 times that of an isothermal absorber. A single stage of in and out intercooling near the middle of the column of the absorber reduces this effect by a factor of 2 at a lean loading close to greater than 0.26. The contactor design for the absorber for CO2 capture has improved from that used for acid gas treating. The larger demonstrations use modern structured backing with larger corrugation angle to minimize the pressure drop while maintaining equivalent weighted area for mass transfer. The earliest absorber designs in capture systems were round. In the Sask Power at Boundary Dam, Saskatchewan, the commercial scale used the rectangular absorber. MHI design at Thompson, the Petronova project, used the rectangular absorber. Probably full-scale commercial designs will probably use a single rectangular absorber to treat all of the flue gases from one boiler. I think So this figure compares the energy performance of 3 stripper enhancement to that of simple stripping. One issue with the simple stripping is that it loses efficiency because of the water vapor that passes overhead and is condensed without heat recovery. Numerous process configurations have been proposed and tested to address this weakness. And these 3 stripper enhancements are the lean vapor compression, the interheated stripper, and the advanced flash stripper. Large-scale commercial applications will probably utilize these or similar configurations to enhance the energy performance. And as you can see here in this figure, the selected lean loading can be used to minimize the equivalent work. At higher lean loading, the working capacity is reduced and the sensible heat requirement increases. At lower lean loading, more steam is required, basically to strip the CO2 from the amine solution. Lower lean loading also enhances and improves the rate behavior of the absorber. The advanced flash stripper has been successfully tested in a pilot plant at the University of Texas at Austin. And as you can see here, the rich liquid solution is fed to 2 heat exchangers in series with a steam heater and to the sum of the stripper. The hot lean solution is retained through the exchangers, and cold rich liquid solution is bypassed through an exchanger to recover the latent heat from the CO2 product. A warm rich liquid solution is extracted between the 2 heat exchangers and combined with the heated cold bypass and fed to the top of the stripper to recover the latent heat of the water from the primary flash here. Because the advanced flash stripper has two bypasses, the warm and the cold and the warm, they can be optimized by adjusting the rates of those 2 streams. So it's possible to recover all of the heat from the stripper overhead. This figure shows the interheated stripper. This is probably an important part of the energy savings process used by MHI in several smaller commercial units and adapted for the 240 megawatt plant at Petronova. Absorption liquid, as you can see here, is extracted from the middle of the stripper and pumped through this heat exchanger. And the hot lean amine solution is in series with the main heat exchanger here. Like the advanced flash stripper, this configuration recovers much of the latent heat of the water from the stripper overhead. This design has no optimization variable, so it's probably is going to be less efficient than the advanced flash stripper. This figure shows the lean vapor compression. This configuration is included with the SASC Power boundary dam project. It has been tested in several pilot plants. It flashes the liquid solution, the lean amine solutions, and the vapors are compressed and returned back to the bottom of the stripper. It's not as flexible as the advanced flash stripper, since the compressor needs to run at a maximum single stage compression ratio 1.8 to 2.2. This figure shows the electricity burden with advanced amine scrubbing, as you can see here. And they are approaching the minimum work to separate CO2 and compress it to 150 bar. The 2 demonstration projects, the one at Boundary Dam and Petronova, are expected to achieve this 210 to 220 kilowatt hour per ton of CO2 removed. The advanced flash stripper is expected probably to reduce this burden by additional 4%. But these process modification or innovations are producing diminishing returns probably, so it's possible to expect that the ultimate requirement 200 kilowatt per ton of CO2 with a thermodynamic efficiency of 56% for commercial units. The energy performance of a liquid absorbent is dominated by 4 energy properties. Liquid absorption capacity, CO2 absorption rate, heat of CO2 absorption, and then the Tmax from the thermal oxidation. The Tmax and the heat of absorption basically determine the compressor, reboiler, and the stripper capital cost and lost work. The rate of CO2 absorption determines the absorber capital cost, the backing requirement, and the loss of work as a driving force. There are other also important properties that also to watch for when selecting an amine: oxidative degradation, nitrous amine formation, amine volatility, amine aerosol emissions, molecular weight, amine cost availability, and amine corrosion. Amine oxidative degradation is a common problem for CO2 capture from flue gases. Even with numerous detailed investigations over the past 15 years. There is not yet a clear understanding of the mechanism by which the degradation takes place. The nitrous amine formation, MHI, and other technology providers, they all have reported successful testing of countermeasures to minimize amine aerosols. But even with these measures, this is still an open problem area. The mechanisms and countermeasures are not yet completely understood. So this is an open area for research and more innovation. So this table,
Mohammed, can you wrap this?
Yeah, so Bibrazine is an excellent.
Another minute.
Yeah. Bibrazine is an excellent absorbent to 7 molal MEA. As you can see, absorption rate is higher, capacity is higher, 22%. Unfortunately, MEA is prone to oxidative degradation. The Bibrazine has the highest rate of CO2 absorption, as I mentioned. But the problem with Bibrazine is the issue of solid solubility. Blending Bibrazine with other amines will give basically comparable properties in capacity and rate and CO2 absorption, but with no issue of solid solubility. So in conclusion, amine scrubbing will be a dominant technology for post-combustion capture. The second generation amine scrubbing provides an improved energy performance, electricity burden approaching 200 kilowatt per ton CO2 in coal-fired applications. The 5 molal Bibrazine with absorber intercooling and the advanced flash stripper should basically serve as the baseline for future improvements in post-combustion capture. Amine aerosol emissions and amine oxidation are not yet completely understood and managed. And thank you. Back to you, Bill.
Mohammed. So again, we'll save questions for the panel discussion in about half an hour. So audience, please submit your questions. We have a few already. The next talk in this session is cryogenic carbon capture by Mourad Younes. Mourad is a science specialist at R&DC at Aramco. He has a pretty established reputation in cryogenic carbon capture and was among the first to develop a cryogenic-based technique that's actually reached commercialization. He has a PhD in energy studies from Paris School of Mines. So Mohammed, or Mourad, go ahead and take it over. Thank you.
Thank you, Professor Roberts, for this kind introduction, and very honored to be among the panelists today. So while my colleague Dr. Mohammed presented you options for CO2 capture with regeneration temperature above 100 degrees C, I'm taking you to a different journey below minus 100 degrees C in this quest of finding really what is a cost-effective CO2 capture solution for our energy sector. So first, let us define the cryogenic space. So we talk about cryogenic CO2 capture, but is it really a cryogenic CO2 capture? So according to the International Congress of Refrigeration in the 1970s, they adopted the CO2 the cryogenic space to be between 0 Kelvin and 120 Kelvin, so which means about minus 153 degrees Celsius. And in this case, we can find eventually air separation as one mean that can be linked to the CO2 capture. Why? Because we can use the oxygen from the air and combust it with the fuel at high temperature and certainly bring these high concentration CO2 flow gases to about minus 40 degrees C at pressure, and then distillate a little bit the CO2 and purify it and reject all the nitrogen and other impurities. So this is the first application where eventually we can talk a little bit about cryogenics. But what about eventually low concentration gases, like, for example, atmospheric pressure boilers or gas turbines? In this case, we need really to go a bit further down in temperature. For the boilers, we will be start capturing CO2 for about minus 100 degrees C to about minus 120 degrees C if we're looking for 90% CO2 capture capacity. In the case of gas turbine, we will start about minus 110 and all the way to minus 130 degrees C, as you can see here. So in this space, it's not really cryogenic space, but in some instances in the literature, we have seen the connotation of high temperature cryogenic. So nevertheless, we will call it cryogenic for our purpose today and follow up these slides. So what happens in our cooling of these flue gases down to minus 120 or minus 100 degrees C? We will be crossing many triple points actually of different substances that could be present in the flue gases. So, for example, the mercury at minus 39, the SO2 at minus 76, the CO2 at minus 56, and therefore that's why we need to capture the CO2 in solid phase. But most importantly, which is abundant in any flue gas, is water, which is at 0 degrees C. This means that we have to take care of all these impurities while we are taking care of the CO2 at low pressure. So it's certainly a challenge, and many companies and research labs were up to that challenge, and that's why they have developed this technology, as we call it, cryogenic CO2 capture technology today, and that's linked to the desublimation. So these technologies are today marketed in the biogas liquefaction, where eventually they use the same process to capture the CO2 and liquefy the methane. So both have similar temperatures, so there is a lot of synergy between these two, and that's why eventually this technology won in this field. Nevertheless, when we look at the utility sector, we are still at the development phase. We have few pilots around the world, but really no large-scale demonstration or adoption at large scale. And that's for a specific reason that eventually we will come to through the slides. So since it's a physical process, so let's talk a little bit about energy and thermodynamics. I believe many of you have seen different variation of the graph here, where you can see eventually the minimum separation energy of CO2. And you can see clearly that we are far from the ideal. So we have seen in the previous presentation energies between 2,000 and 4,000 eventually kilojoule per kilogram, while the minimum separation energy is more around 200. And that's because of lots of irreversibilities, because we have to deal with so many things along with the CO2. And one molecule that we have to deal with is water. So we can see that water minimum separation energy is high, considering the high content of water in the air. Nevertheless, when we report this energy to the kilogram of CO2 capture, it reflects to about 30 to 100 kilojoule per kilogram that has to be added to the 200, right? So if we're looking at physical processes, we will be looking especially refrigeration processes, which is the case here about cryogenic. We will be talking about ideal coefficient of performance or Carnot coefficient, right? So here I have plotted in the area of interest on the evaporating temperature between minus 100, let's say, to minus 130, what would be the ideal coefficient of performance for various condensing temperature. And we can see that in the area of interest to us, especially in the utility sector, we will be ranging between 0.85 maybe to 1 in terms of ideal coefficient of performance. So if we take 60% efficiency on this ideal, and considering the desublimation energy of CO2, we will end up with an energy penalty for about 1,000 to 1,200 kilojoule per kilogram. And this is, we're talking here about electricity compared to other technologies that could be requiring heat or a combination of heat and electricity. The good thing about capturing the CO2 in solid phase is the possibility to melt the CO2 and then compress it in liquid phase. And liquid compression certainly is much more cheaper than gas compression. So we'll be saving on capex as well as on energy demand. As you can see, it's just 10 kilojoule per kilogram versus 300. So this is one of the areas where eventually cryogenic systems could be more adapted to some of these applications. So how these processes work, here I have shown a little bit an overview about eventually cooling the flue gases down to the CO2 capture temperature. And I presented 3 hypothetical stages. So the first one is about water and impurities remover and the hypothetical interface at 0 degrees C. And then sensible cooling up to the hypothetical, let's say, temperature of -100. This is where eventually we'll be starting capturing CO2, and then the CO2 capture part towards the end. So regarding the water or impurities, certainly we can remove them completely or partially, depending on how we want to deal with them and what system we would be using. As for the sensible cooling, we have as well two options here. Either we go with indirect contact heat exchanger like gas-solid interface, or with direct contact heat exchanger with gas and liquid interfaces. And towards the end, going to the CO2 capture, certainly we need a refrigeration system, which will be the heart of our CO2 capture system, as well as a way to contact this coldness with the CO2, so either through a solid-solid interface or a solid-liquid interface, for example. So zooming into the first part of the process, we can certainly remove the water with various means, right? They are all commercial. We are using them in the air separation units today. They are good, they are commercial. They will avoid any further processing requirements for these impurities downstream and avoid freezing and having to deal with solids other than the solid CO2. Nevertheless, they could be capital intensive or would require a lot of integration with the process if we have to make them really energy efficient. The other approach is to take a partial capture. So for example, here we're talking up to 0 degrees C, and in this case, we will be capturing water in liquid phase, and still about 5 grams of water would be remain in the flue gases, which is still significant that we have to deal with in the following stages, and therefore it will add complexity to the system, but could eventually lead to lower energy penalty. So there could be a trade-off between the application on which way we want to go forward with at least the first stage of removing impurities and removing water from the system. So moving down the temperature, we have to basically cool down the flue gases to -90 degrees C, right? And here either we can use the very well-known aluminum brazed heat exchangers that are used in the cryogenic space, and this heat exchanger will avail certainly a very low temperature pinch and a lot of compactness. Nevertheless, they can accumulate pressure drop if you're not removing all the contaminants because of the deposition of the various impurities in the stream. And most importantly, they could be cumbersome at large scale when we have to deal with a lot of headers and collection of headers. So this will require a lot of manpower for welding and all these things, so which increase eventually the price of these heat exchanger or of the system. Nevertheless, in terms of cooling, they will be very effective, no stream contamination, and potentially can integrate as well a part of the refrigeration system along the flue gas cooling. So the second option is to go with direct contact heat exchangers. So here the ask is a bit more difficult in terms of finding the proper liquid that has to contact these flue gases down to the required temperature. It will be effective, certainly. Capex of direct contact heat exchanger is very low. So it could be economical solution. Nevertheless, we have to deal with the liquid medium losses and possible contamination of the CO2 or of the liquid that's in direct contact with the streams, and then it has to be regenerated at one point in time. So I will come back to this eventually and the capex later on towards the end, as Professor Gibbons indicated. At one point in time, depending if we're designing for a base load application or for a peaker, then eventually you would look at optimizing your system differently, right? And this is a perfect way to say, okay, where do I want to spend my capex? Would I spend it here or somewhere else, depending on how many hours I have to run my system? So moving down the line, we get to really the heart of the system, which is the refrigeration system. So this is eventually where all the irreversibility are produced in a way, or this is where we need really to be very effective and efficient in terms of cost and in terms of energy penalty. So various architectures are in the literature regarding how to go down to low temperatures. Here on the left-hand side, for example, you can see here we have a first loop, then a second loop, and the third loop of 3 different refrigerants eventually, 3 different compressors. Here are the condensers that would be integrated differently in the evapocondensers, and to get eventually to the required temperature for the CO2 capture here towards the end. Another way of doing this is eventually coupling these compressors and these loops on the evaporator side of the upper loop, and then the condensing side of the lower loop. And then again, you will have a system where you can get to low temperature. It could be a different choice of refrigerant, and in both these two systems, it will be easy to operate in a way. Could be nevertheless capex intensive, because we are dealing with 3 compressors or 4 compressing depending on the temperatures, and these compressors certainly are not cheap. Another way to do deal with this, you can go to an integrated cascade system. So here we have certainly, as you can see, a lot of piping, but nevertheless we pay less on the compressor. So again, it's a trade-off between what we want to achieve and what we don't want to achieve. So briefly, to summarize how these integrated cascade system work. So the fluid is compressed and goes into a condenser. So it's a blend of refrigerant. So it's not a single component refrigerant, in opposition to these two systems where we can eventually have single component and therefore a constant evaporating temperature. Here, certainly it's a blend of refrigerants, so we'll be having at the evaporator a temperature gradient while we are evaporating our final fluid. So we will compress our refrigerant, partially condense it, having it separated, and then the vapor phase will be condensing again partially to another separator, and then condensed further into eventually a final expansion stage. And this is where we eventually will provide the cold energy, and then we go back in the system all the way up, depending on how we want to go and how much energy integration we want to do into the suction of the compressor. So I'm not saying that this is the best configuration. I'm just saying that this could be eventually different possibilities, different refrigerant that could be used, and different operating points and different controls and different capacity. Just one point regarding eventually this final stage that is really important, right? The CO2 capture part is how the enthalpy gradient would look at our evaporator when capturing the CO2. So here I'm showing the CO2 saturation pressure function of the temperature. And you can see, for example, in the case where we are taking a boiler, for example, flue gases, capturing the CO2 between -100 to -105, or between -115 and -120 is totally different, right? So if we will be able to capture 5 times more energy in the first degrees of CO2 capture compared towards the end, right? And it's not linear. So if you have a fixed evaporating temperature here at -125 or -130, it means you have a lot of irreversibility, especially for the highest demand of energy, which occurs at the first 5 or 10 degrees C of your CO2 capture. So this means that either you have to work with a blend of refrigerant, and then your penalty will move from the evaporator side to the condenser side, or you have to operate in a 2-stage eventually expansion system where you would expand to a first pressure, let's say at -110, capture a little bit what's at the high temperature, and then have a different level of pressure at -125, let's say, and capture the remaining CO2. Certainly, this will increase the capex, but it will reduce eventually it will increase your efficiency, but it would reduce certainly your penalty on the CO2 capture cost. So therefore, it is important to know what we want to design for and what system we have to operate, and bear in mind eventually the capex that we have endured for our system to know how to design it. So moving forward, we get to the CO2 finally. And then here we are at -100 degrees C, we're getting into our heat exchangers, and we have the CO2 who will desublimate or go directly from the gaseous phase to the solid phase. And here again, we have different ways of dealing with this. So some people have looked into expanding the gas and try to generate like solid particles that they will try to collect and recirculate. Nevertheless, if you are on the temperature entropy diagram and you are on the right hand side of the diagram, so you're in the gaseous phase and you try to expand, you will only generate a little bit of solids, right? So this means that you have to recirculate a lot of gaseous CO2 at very low temperature in order to get the required CO2 capture efficiency. So, and therefore we have not, I personally have not seen any system that were developed based on this principle beyond just lab works. So the other two techniques that eventually were piloted or brought to a higher scale are the solid solid heat exchanger, which is in this case indirect contact heat exchanger. And this is a photo of previous work I have done eventually, where you can see the solid CO2 freezing, or like only water freezing on any heat exchanger. And the benefit of such a system are certainly there is no cross-contamination between the fluid and your CO2. And nevertheless, the drawback is once you have solid, you have to deal with your solid. So either with a rotary process or a batch process, and this will certainly increase your the surface area of your heat exchanger, and then the capital expenses spendings, right? So the other way to do it, and this is where eventually a few companies are working on, and here I'm showing a patent that's filed from KAUST, where they have designed an elegant heat exchanger with a direct contact between a refrigerant, let's say, or a cold carrier or carrier fluid and the CO2 or the flue gases. And in this configuration, they try to maximize the heat and mass transfer and reduce eventually the entrainment of the particles, and then reduce the cross-contamination, which is usually one of the drawbacks of these solid liquid contacts. So depending on eventually how you want to what you have in your feedstock as well, right? So we talked about impurities, we talked about SOx, we talked about eventually water and mercury. So mercury has to be removed early on if we have aluminum heat exchangers, because aluminum and mercury doesn't go at all together. So this means that depending on your initial condition of your flue gas, you have to decide to go with one configuration or the other configuration, and there is no one single configuration that will be beating everything for all applications. And this is the case actually for any CO2 capture technology. So we don't have a silver bullet, in my opinion, and the right CCS will depend on the ambient conditions, will be depending on the CO2 concentration and the flue gas that we're designing for, the impurities and the CO2 concentration, and the CO2 end use. For example, if we're looking at the liquid CO2, or are we looking at CO2 for EOR applications with very stringent, for example, oxygen content, or if we're looking at CO2 with less stringent specs, for example, in saline formation, your choice for your CO2 capture system could be different. And another parameter, for example, is the size. If you're designing, depending on the size, some systems are scalable while others are not. The availabilities of auxiliaries. So in some processes, you will need just electricity, which is the case, for example, of cryogenic CO2 captures, while other you might need a combination of electricity to drive the pumps and the compressors and the fans, as well as steam, for example, to regenerate your solvent or sorbent or whatever medium you're using. And last but not least, the load, right? Are we operating for high load, low load? Then the capex will become important, and then this is where eventually you would decide to go with the system with the lower capex. So with all these parameters, if I want to try to map our cryogenic technology, we'll certainly find that we have a lot of areas where cryogenic system will make sense, right? In terms of sensitivities, we are sensible a little bit to the second degree to the ambient conditions, especially if we're doing a lot of heat integration in terms of system design, but at the cost of capex, certainly. In terms of CO2 concentration, the higher the CO2 concentration, the better it is for cryogenic systems. In terms of impurities, I think all CO2 capture systems have to deal with impurities. We're not forming stable salts or any oxidation. It's just a physical process. So we will have to be physically able to capture or deal with these impurities and get them out of the CO2 at one point, or out of the way of the CO2 while reaching -100 degrees C. As for the CO2 end users, we have seen that if we are looking for a liquid CO2, certainly the process will give you a liquid CO2 readily. If we're looking for gaseous CO2, here again, compressing the CO2 in liquid form is much easier than compressing it in gaseous form. And this is where potentially we can have some savings. In terms of size, it will depend on the size of the refrigeration system as well, and the choice of the technology that we'd be using for the sensible cooling or for the CO2 capture. And this is where eventually the system could be sizable or not, scalable or not, it could be modular. And the last point is the auxiliaries, where potentially, since we're using just electricity and it could be integrated with any electric grid or post retrofit application, there is very little eventually disturbance to the existing power plants, and eventually we can use it in the future. All these, we talk about these excess energy with Professor Gibbons, right? That we can power or store some of the cold energy required for the CO2 to capture eventually as a CO2 later on during the day. So we can combine a little bit of energy storage with our cryo systems and using low-cost electricity, but certainly up just to a specific limit. So with that, I will end my slides. I know we're running over time and I'm trying to expedite my talk. So thank you very much for your attention and looking forward for the questions in the Q&A session. Thank you.
Thank you, Dr. Younes. Thank you. So in the interest of time, we'll move on to the last talk in this session. So Professor Song is from Tianjin University. He received his PhD from Tsuba, University of Tsuba in Japan in 2013, and worked at the Collaborative Research Center for Energy Engineering at University of Tokyo. So he's going to give the last talk in this session on low temperature capture integrated with use. Professor Song, are you up? Good. Thank you.
Okay, hello everyone, can you hear me?
Yes, we can.
Okay, I know this is afternoon from in Arabia, but you know, here in China, it's evening, so I don't know, I should say good afternoon or good evening. My name is Chunfeng Song. I'm very glad to join this online conference to talk something. I'll introduce something about cryogenic CO2 capture and its application. And just now I have listened to the interesting topic from Younes. So actually I have the same research interest, also focus on cryogenic CO2 capture. And I know maybe we are too much time over time, so I will use quick time to introduce my work. And actually, first is background. As we know, in the worldwide, especially in China, every year we will discharge a huge amount of CO2 due to, for example, fossil fuel utilization. So actually, in China, we have a very targeted requirement to reduce CO2 emission and control CO2 discharge. So actually in China, we have so many scientists and researchers focused on the research related to CO2 capture, storage, and utilization. And as we know, just now we have several professors has introduced some different technologies, for example, CO2 absorption, and of course we have some other choice, for example, membrane CO2 separation and the cryogenic, also named low temperature CO2 capture. And based on this, we can separate CO2 from industry emissions, for example, coal-fired power plant and the cement plant and some other where. And then actually we have two choices. And the first choice is to storage CO2. And the other choice is reuse. Means we can transfer CO2 into, for example, bioenergy or biomaterials or some other resource we can reuse in our daily life. So actually this is the whole roadmap. So CO2 capture and storage and utilization. And my interest actually is focused on the CO2 capture by low temperature technology. And we also name it cryogenic CO2 capture. why I focus on low temperature or cryogenic CO2 capture. Actually, we know most of CO2 discharge or how to say emits from high temperature condition. For example, from the flue gas from the coal-fired power plant. So actually, normally we can consider some middle temperature technology or high temperature technology to separate CO2. But as we know, after we separate CO2, we need to compress it and transport it to the storage site or utilization site. So in this stage, we need to high purity CO2. So if we choose cryogenic technology, actually we have some advantage. For example, we can obtain high purity liquid form CO2 or solid form CO2. So that's why I focus on the low temperature CO2 separation technology. And just now, Professor Younes had introduced some conditions for cryogenic CO2 capture. Here, I want to also mention something. For example, actually, if we choose cryogenic technology, its energy consumption or energy requirement is highly demands on the CO2 concentration in the flue gas. So that means if we use cryogenic technology to separate low concentration CO2 emissions, actually we need to consume more energy. But if the CO2 concentration is higher than the normal condition, in that case, we can use a less energy to separate CO2 by cryogenic method. So based on this, I designed equipment to separate CO2, for example, from the flue gas or raw biogas. So here, this is the structure of the system I designed. In the whole system, I use 3 steering coolers to generate a low temperature condition in the system. And in the first tower, I named it perforating tower. Here, I can separate the condensate water from the flue gas or biogas or some other raw gas. And then I can introduce the dry flue gas into the main freezing tower. And here, under the minus 100 to minus 80 centigrade condition, the CO2 can be separated in the solid form and frost on the heat exchanger. And then we use scraper to separate the solid CO2 and storage the dry ice in the storage tower and take it out. So this is the real picture of the system I designed. And here you can see this is the main freezing tower and perforating tower and the storage tower and the control panel. And also I tested the different CO2 forest density change process. And this is the real picture. And here you can see the dry ice we obtained in the system and from the gas phase to the solid phase. And actually, energy consumption is a very important factor for different CO2 capture technologies. As we know, if we want to apply each technology in the commercial condition, we need to overcome the challenge of the energy consumption. So I also investigate the energy consumption of my system. So you can see in the life scale, we can separate most of the CO2 from the simulated flue gas and use around 0.6 electrical energy to capture the CO2. So at least in the life scale, the energy consumption is not so high. But if we want to enlarge the scale, maybe the energy will increase. So it's not enough. Based on this, I designed the cryogenic combined with the other method. So just now I mentioned we have different choice, and for my choice, in my opinion, I want to combine cryogenic with some other, for example, absorption or membrane or other absorption process. So I tested different arrangements, for example, cryogenic and membrane, cryogenic and hydrate, and cryogenic and absorption. And one interesting is that when we test membrane combined cryogenic, this is a simulation result. We found a very interesting result. When the CO2 concentration between 10% around 30%, the energy consumption of the membrane and cryogenic process is lower than MEA process and pure membrane and pure cryogenic. So that means if we want to combine the cryogenic and the membrane together, it maybe need less energy than the other technologies. And also we test the different membrane materials. So here this result is the performance of the membrane. So you can see under the low temperature condition, the membrane selectivity of CO2 is higher than the higher temperature, room temperature, or high temperature. So that's very interesting things. And we also test the mechanism why this energy consumption of the membrane at the low temperature condition is lower than the room or higher temperature. So based on this, we update our system. We put a membrane module in our system to increase the CO2 concentration in the flue gas. And then under the high CO2 concentration, maybe the cryogenic temperature will be higher than the previous one. So that means we will consume less energy in the update in the hybrid system. This is our experiment setup to test the different membrane materials and the low temperature box. So you can see for the CO2 selectivity, it will be increased under the low temperature condition. And also we combine we have combined our results with some Chinese companies. This is a Chinese National Offshore Oil Corporation, and because every year they will import some liquefied natural gas from the abroad, and when we use the liquefied natural gas, a huge amount of cold energy will be discharged. So actually, if we want to use cryogenic ether in the industry, we can reuse this part waste cold energy as the cold energy source. And of course, we have applied our idea in a Chinese wastewater treatment plant to update the biogas. So in our process, we can obtain the food grade liquefied CO2, and at the same time, we can obtain the high purity biomethane, namely bio-natural gas. So that's the good result. And now, actually, we also invest some other choice to combine, for example, cryogenic with adsorption process, because we found some POM materials, their performance under the low temperature also better than the room temperature. So that's very interesting result. Means we can combine the cryogenic system with adsorption process together. And we also combine the different methods based on the energy consumption. So we can see this in the red color range, we can see the cryogenic-based hybrid system can perform lower energy consumption than the normally adsorption membrane and the absorption process. So actually, for the future trends, in my opinion, after we capture CO2, actually we need to reuse it. Now we have undergoing a Chinese government project to use the microorganism to transfer the high purity we capture CO2 into biomaterials. So in the future, we want to build an artificial carbon cycle just like this. After we capture the CO2, we need to transfer it into, for example, biofuels and bioprotein and biocarbohydrate and the other useful biomaterials, biomass. So that's all. Thank you for your attention.
Thank you, Professor Song, and all the speakers in this session. So now I'd like to open it for a panel discussion. So if you can, yeah, good. Good. So most of us are here. So we'll take questions from the audience, and then I'll take the Q&A from the chat. So are there questions in the audience? Yes.
Yeah.
Okay. So thank you, gentlemen, for your presentation. Just actually, I was wondering when would I see the biomass part, which was the last slide from Dr. Song. So basically, for a place where we have a lot of desert and too little biomass in our sand or soil, so I mean the idea of converting most of the CO2 into a biomass should be one of our key objectives. So I noticed that it was the last, maybe it's not the least, but maybe there was no expansion. Can you expand on that? And what are the real efforts in that direction, if I may?
So any of our panelists want to answer that one?
Okay, I think I can discuss the just now's question from my opinion. Actually, as we know, for example, for China, every year we discharge around 10 billion tons CO2 due to fossil fuel utilization. So, of course, we can develop different technologies to capture CO2, separate CO2. But after we separate or capture CO2, how to treat the huge amount pure CO2 is another problem. So, actually in China, how did we do? Actually, the first choice is not storage, because if we want to choose the storage option, that means there is no additional value. But if we reuse the CO2, just now I mentioned, we can, if we transfer CO2 into biomass, maybe we can generate some additional value. For example, biofuel, bioprotein, and biocarbohydrate. And actually, I have an example. Just now, I mentioned I'm undergoing a Chinese government's project. Now we separate the pure CO2 by cryogenic method in a Chinese chemical industry, chemical plants, and then transport the pure CO2 to agriculture area. And here, the farmer from China cultivates the microalgae, use the pure CO2 to generate algae biomass, to generate some bioprotein. And then finally, the bioprotein will enter our human beings' food cycle, food chain. So that's an example how to combine the CO2 capture and the bioenergy or biomass together,
Thank you.
Can I make a comment?
Other questions? Yep, please.
Yeah, unfortunately, you have to do the sums, and the sums are that you're trying to get to net zero CO2 emissions, and it's CO2 emissions to atmosphere that matter. And if you follow through the chain that you're talking about, yes, you can put CO2 into biomass, you can put it in food chains, you can even put it in trees in the soil, but long before we've got to a resolution on the climate, which will take thousands of years, that CO2 is going to end up back in the atmosphere. The real problem is you have to put a value on not putting CO2 into the atmosphere essentially forever. You have to put a value on permanence of storage. And yes, if we don't have that value, why would you do it? But if people really are trying to get where we need to get, according to the climate science, you have to be rigorous. You have to think, where does that carbon eventually go? And will it be permanently locked up there out of the atmosphere and the oceans for an indefinite period. And if it isn't, it's no use for climate. You know, we had an example of people doing Amine capture back in the 1980s. They weren't doing it for climate. They were doing it because we had an oil crisis, if you remember. We were on different sides of the problem there. We were trying to get more oil out of the played out fields in the US to replace Middle East oil. We're on the same side now, but we share an atmosphere, and CO2 cannot go into the atmosphere directly or indirectly.
Right. It's all a matter of time scale, right?
And the time scale for the climate is basically the time scale of mixing in the deep oceans, and think 10,000 years.
Okay, so good, thank you. Bassem.
Thank you all for the talks. I have two questions. Perhaps the first one for John. It's easy to look at what the UK would do, but what are we going to do with the third world countries? Sometimes when they have their own indigenous coal and no other resources, say Indonesia, for example, and because the projection of the drop in the coal usage obviously makes some assumption of what would happen to these countries. And the second question is, if I can, the kingdom relies heavily on gas turbines to generate its electricity. So based on all these technologies, what is likely to be the most cost-effective capture technology, at least in the short term?
There's two questions there, and there's one of equity and what can people do. The only problem is that the climate will not be influenced by any arguments we make. We say, people say, well, we should have a chance to emit CO2 like Britain did. We were the first to emit large amounts. The climate doesn't care. All the climate cares about is how much CO2 goes into the atmosphere. So we're in a different world. We're a world with climate change potential. We're a world where you may not be able to use coal and just put the CO2 in the atmosphere as we did. We're also in a world where we no longer use steam pumps as we did in our mines with a 0.5 percentage point of thermal efficiency. We can run power plants even with carbon capture and storage that are probably 10 times more efficient than the ones that Britain industrialized with. There's different potential. People can get solar power at almost probably the fuel cost of coal. So it's a different world. I don't think you can say, oh, we want all of the good things, which is the ability to put CO2 in the atmosphere and not care about it. You want that, and you don't also reflect that you've got a whole different balance of things. Of course, if you want to get to net zero, it just is not optional that you run any fossil fuel with CO2 capture if you want to get there. But I have to say, if China and the US are going to take it seriously and get there, and they consider net zero to be in their essentially security interest, whoever else you are, you're going to have to do it. It's not going to be negotiable. Something will have to happen. And then the quick question about what can you do on gas turbines if you're in a hurry and you want to go now, go post-combustion capture. It may well be that post-combustion capture actually proves to be cheaper in the longer run by analogy with limestone FGD, that we did actually stay with the default technology. And our friends in China made it an awful lot cheaper. Yeah, I'd give somebody else a go. Sorry to talk so long.
Good, thank you. The other panelists want to comment before we move to the next question? Okay, so I'll take a question from the Q&A panel. So this one happens to be for Professor Gibbons as well. Do you think biomass from forest waste from cleaning for fire hazard reduction will be enough for the expected increase in biomass demand? Some places are actively cutting down forests for biomass. This diminishes their potential CO2 capture and storage time. Is there any regulation regarding this?
Well, there's certainly regulation on sustainable source of biomass. Sorry, does anybody else want to comment? Okay, so there's regulations on sustainable sourcing of biomass, which imply that effectively over time, any biomass used will be replaced. That's if you're using it as a fuel in the UK or other places where it's subsidized. So that's there. But the question about forestry waste, I think it's a very good idea to do something with it that will lock the carbon up. As I say, you don't want the fires, that will release the CO2 from atmosphere. what do you do with it? You know, what else can you do with biomass to stop the carbon ending in the atmosphere in a short enough period of time to be immediate as far as climate change is concerned? But I don't think we will have enough biomass. No, I think once people take net zero seriously, you'll see a huge demand for carbon dioxide removal. And it's relatively cheap. You know, you might effectively, you know, if you take a barrel of oil, $60, $70, whatever it is, a barrel of oil gives half a ton of CO2. If you can take CO2 out of the air for even a couple of $100 a ton, which I think people might think they do, you're adding $100 to a barrel of oil. Now, a barrel of oil is a very, very useful commodity. And we've seen some pretty high prices. And we've also seen some big increases in the efficiency with which you can use it. So I think we'll see a huge demand for carbon dioxide removal to get a circular carbon economy by using the atmosphere on the way. And there'll just be a huge demand. And all this stuff about, oh, you can't do this, you can't do that, you can't do the other, you know, you can't drive a petrol car, you can't eat beef, you can't fly. It's true, you can't, unless you pay the environmental cost of doing that. And a lot of people can afford that and should pay for it. So anyway, I'll shut up again, sorry.
Thank you. Chris Wagstaff, you've asked 4 or 5 questions, so I'll let you ask one of your favorite ones. Yeah. Okay.
Sure. I don't know if you necessarily have an answer, but it was a curiosity. So I read a clickbait news article proposing carbon capture directly from oceans, and assuming that it would be in equilibrium with the air instead of direct air capture. Is that in any way? Oh, sorry. Is that better? Would it be ever feasible to do direct carbon capture from oceans instead of from the air, or is that kind of a silly idea? Any takers?
I can comment a little bit maybe on that. So I'm certainly not an expert on ocean CO2 capture, but I have seen as well a lot of now an emphasis that's starting, you know, on talking about capturing CO2 from the ocean. So technically it's feasible, and you can eventually combine some of the direct air capture processes equipment with the water in order to capture the CO2. Certainly the CO2 concentration into sea is lower than the atmosphere because, you know, CO2 goes usually from the atmosphere to the sea. So you would be expecting to have a higher energy penalty. But nevertheless, what could be interesting is that in many cases, we are already moving large amounts of CO2 of seawater for various applications, right? Whether cooling or desalination or doing something with it. And then taking these amounts of water that are already processed and the energy of pumping paid for and combining them with CO2 capture could eventually lead to a CO2 capture costs that are competitive with direct air capture. So this is roughly my take on that.
Thank you very much.
Thank you, Mourad. Anybody else want to comment on this? Okay, so here's a question for all the panelists. So, we are providing, are we providing equal attention to carbon capture, utilization, and storage of the CCUS problem? Or are we biased towards the simpler of the problems, which is the capture piece? So are we spending enough time and effort on the utilization and storage? Or do we have to capture it first and then we'll worry about the downstream problems after? Is it a sequential problem, or is it we're tackling the easy problem first, or is it a combination of both? So anybody that wants to comment?
I'm happy to start with the answer. So having more CO2 available and growing the market of CO2 actually will be a push to do something with the CO2. And one approach is to produce hydrocarbon fuels by recycling the carbon. If the original CO2 comes from combustion of fossil fuels, of course, and then it goes eventually, even after the fuel, it goes to the atmosphere, we end up with those emissions. but the carbon is retained for longer in some systems, technical systems, which slows down the emissions. Now, in the solar fuels area, we aim at CO2 capture from the air in balance with emissions. So in the circular economy, we would balance carbon in, carbon out, and the tough part is to reduce CO2. It's a highly energetic, it requires a lot of energy, and it's not easy to do it in electrochemical processes because of coking and all other issues. So here we have some processes to reduce CO2 using thermochemical processes, again, similarly to water splitting. This has been demonstrated on sun, all the way from air and from air to CO2, water, then splitting to solar kerosene at small scale and also at an intermediate scale at a solar tower at IMDEA Madrid. Still, there are not enough players because many researchers will say, we have lakes of water, but we don't have a lake of CO2. So it's challenging to invest in that field. If we have now large streams of CO2, I'm sure there will be more researchers and industrial companies willing to invest. And once the wheel starts spinning, it will move on its own. The danger is in the long term that if that wheel will be spinning on CO2 from coming from combustion of fossil sources, and that will not slow down the use of fossil sources, because people will think that, okay, we have those CO2 capture and utilization technologies, we don't need to eliminate the fossil fuels. So these are different aspects, but definitively it will help if we have CO2 provided to start to grow the research on using the CO2.
Okay, good, thank you. Other panelists want to opine?
Yeah, I can talk about it here, Bill. So there is much focus on the CO2 capture. The reason why is because it's expensive. If you look into the value chain, the capture and the transport and the injection, whether you use the CO2 to making chemicals or use the CO2 for enhanced oil recovery or for storage, really the expensive part is coming into the capture. And this is why really much of attention is more into that. So to bring the cost down, to be able to deploy CCS at scale. So either you really work, bringing the cost down, or you provide some incentives, financial incentives to make it, deployable, at the scale. Transporting CO2, the technology pretty much mature. Injecting CO2, we have been doing it, for decades. We inject, the CO2 EUR, has been, since the 70s. We inject the CO2. There is not much really to know about it, So really the innovation is coming really more into the capture part. This is why we need to improve the Amine process, the solvent, the cryogenic, looking for adsorbents, membranes, etc., to make it, cheaper, to make the CCS, reliable and deployable. Thank you.
Thank you, Mohammed. Others? Okay.
No, I can second maybe Dr. Mohammed that eventually from the technology point of view, we need to create maybe a big step towards achieving low CO2 capture costs. So on the transport, there is just only such that can be done. We consider the compression certainly part of the capture. Now injecting or storing CO2 underground, I think this is something that now the industry have gained a lot of experience and had many projects and demonstration and commercial plans. But the question for the storage remains eventually monitoring the CO2 and who's taking the liability, which becomes more political than technical. Going back to the U part of it, certainly now with the introduction of the circular carbon economy, would be prone to have more CO2 in our economy and recirculate eventually the CO2. But the economy would only take just a part of it, right? and it will be probably one digit % of the total CO2 that's generated, and therefore it is in terms of order of magnitude less important than the storage if we have to talk about these gigatons that Professor Gibbons showed earlier to reach net zero. So therefore we are certainly looking into the capture as an industry, not certainly as to the Aramco, as well as many companies, universities are looking at the conversion of CO2 and doing a valuable product out of the CO2. Thanks.
Thank you. So another question from the panel. Oh.
Can I just comment on the storage, Bill, just very quickly? I mean, I think it is interesting that the cost of storage can be prohibitive and dominant in some places. So, for example, if you're not in the right place, storage can be very expensive, and capture still easy. And also, if you're not running for very long, transport and storage system, if you're only using it 5% of the time, it becomes very, very, very expensive. So, we kind of say traditionally for baseload, where you've got access to storage, yes, it's not very much, but it can be an insuperable barrier. And just to sort of go on to the same theme, this is where direct air capture gets interesting. Conventional direct air capture with geological storage, because you've got a bit of a time averaging in the atmosphere. Although your capture now is very expensive, relatively speaking, you can run the plant 24/7 or as much as it'll run, and you can place it somewhere where you've got CO2 storage that's readily available in large quantities. So at that point, you sort of go back to this paradigm of having very expensive capture and very, very cheap transport and storage. But the alternative would have been somewhere where you might have relatively cheap capture, but absolutely impossible transport or storage, or you're up in an aeroplane or something. So it is interesting how that works out. And obviously the other thing that you were seeing is people taking hydrogen, or thinking about taking hydrogen to places instead of bringing CO2 away. So Japan, for example, is one of the places that's really looking actively at using hydrogen, because they've got to bring the fuel in and take the CO2 away otherwise. It's quite a complex sort of scene, really, and very much location matters.
It's like real estate, location matters. Thank you. So now kind of a general question. When we store CO2 underground, are we going to create oxygen deficiency above ground, considering the amount of CO2 we need to store?
I think the oxygen deficiency will come from just linking the carbon to oxygen and creating CO2, and not the fact of storing CO2 underground, because I don't think we will be able to create put so much CO2 underground to be to reduce the CO2 concentration in the atmosphere below the pre-industrial era, right? So and we're talking about ppm levels, so which means that all the vegetation probably will still continue operating as they are doing, and creating the required oxygen eventually in their cycle, and cycling between CO2 production and oxygen production. So I think it's not related to the storage more than related to the consumption or linking the oxygen to the carbon or the fossil carbon.
Okay, thank you.
I'm sorry. Actually,
Jon, yes?
in my opinion, it actually is not necessary to worry about the oxygen concentration, because actually we capture CO2, or we store the CO2, or we use CO2. The amount compared to the whole carbon amount in our environmental cycle is just a very small part. So actually the oxygen concentration or the other gas maybe will not change in our atmosphere, I think.
Okay, thank you.
And
Other questions from the audience? Awesome.
Maybe a quick one to Wojciech. I just wonder if you could rank where the solar thermochemical sort of technology would fit among what we heard today. And would it be better to sort of produce, say, hydrogen or other commodities instead of doing what you were suggesting?
Well, I was talking today about solar thermal CO2 capture, which is, to capture CO2, you still need to put some energy there. So if you drive it by renewable energy, in this case solar thermal, that reduces the energy that otherwise you will take from fossil fuels. But solar thermal is also very much suitable to process that CO2 once you have it, and to make synthetic fuels so that you can displace petroleum-based fuels with synthetic fuels made from water and capture CO2. Eventually, this is a solution that brings us closer to the circular economy. What we put into the atmosphere, we should take it back and we should re-energize. And the nature is a good teacher, right? So this cycle has been there since the beginning of life on Earth. Maybe as a photochemical process, not thermal, but if we use renewable energy to re-energize, and then we can use these fuels without feeling guilty that we pump, the product gases into the atmosphere if we take them back. So it's there is a interplay between solar thermal, carbon capture, fuels, and also some other processes at industrial scale, where CO2 comes not necessarily from combustion, but from chemistry of processes such as lime production for construction materials. And we know that during lime production, CO2 is liberated quickly, but it takes a long time to bind it back into the structure of cement, for example. So there is a large spectrum of opportunities for solar thermal to match. Yeah.
Thank you.
Okay, looking at the time, we're exactly on time. I want to thank all the panelists and the speakers. It was a great, very informative session. I really appreciate your insights. There are still some questions that are fairly specific. If you'd like to answer those individually, the questioner might appreciate that. So I'd like to thank the speakers again and close this session. So thank you very much, gentlemen.
Thank you.